you everyone. I'm Enrique García, technical manager from Airbus CRISA. I would like to show you to everyone, also the ones that are online, the current working that we are developing under Airbus CRISA, the GR740 Payload Control Module, or PCM. So in the next slide, I will show you the background of this work, also the architecture, and the development plan for this processing module. So beginning with the GR740 PCM, what is this processing module? It's, from our point of view, it's a very high performance module based on the multi-core GR740 and the flash-based FPGA from Microsemi, the RTG4. So as you know, the development cycles are every time more and more tight. So we conceive this processing module as a general purpose controller board. So in a single hardware design, by adapting the hardware at manufacturing level, we expect that we can give answer to the current mission needs and also to the future mission needs. This is achieved by two means. Firstly, because of the flexibility provided by the FPGA, we can reprogram the code at the latest stage of the mission. Also, because of the high number of controller interfaces provided by the microprocessor. And also because this board will be fully compliant with ADA initiative, as in other presentation has been already introduced. ADA is which stands for Advanced Data Handling Architecture, is an industry collaboration initiative to achieve a modular avionic with very versatile modules and with interchangeable modules. So in the right side of the slide, we have an example of an ADA architecture, in which we have a pocket module, and a system slot, and range of peripheral slots that can be used, for instance, for a mass memory, for thermal control, or for analog input-output, just to name a few. In the case of the GR740 PCM, will be act as a system slot or processing module. ADA standard is based on compact PCI serial for space. So the form factor of this board will be that one, based on the 6U, the form factor. So we started this board as an internal R&D in the mid last year. Okay, this design had a lot of synergies from Payload, which stands for Precise and Intelligent Landing by using onboard technologies. It's basically a project with the main purpose of guaranteeing a global access to the lunar surface by landing precisely and safely. Our contribution was the landing processing unit, or LPU. On the right corner of the slide, we have a mechanical drawing of this unit, which was mechanically speaking ADA compliant by using the same form factor from compact PCI serial for space. That unit was composed of the power supply board and the GR740 PCM. The Payload, of course, also the LPU was going to be embarked on the Luna 27 lander as an ESA and Roscosmos collaboration. Unfortunately, the Ukrainian war started, so eventually the Payload project was cancelled, so was the LPU. So despite this bad news, we took advantage of that cancellation to review the architecture, to review the potential improvement of the architecture. And this reevaluation of the architecture was also driven by the new specification of the ADA standard. So right before Payload cancellation, we had the electrical design finished with the PCB design well advanced. As I said before, the mechanical concept was taken from ADA with a 6U form factor, and which means a standard depth of 160 millimeters and a pitch of 5 HP, which is more or less around 25 millimeters. But this architecture had some flaws regarding the ADA standard. The first one was the backplane connector that was not compliant with the standard, and the other one was the main internal power supply, which was done with 3.3 volts instead of the 12 volts. So we evolved the architecture that it is on the right side of the slide. I will go through directly to the evolved architecture, and I will introduce you the architecture as it is of today. So basically, what we have here is, as I said, the GR740 microprocessor as the central part of the board, connected through 4 spaceware links, directly connected through the spaceware router of the GR740. We have a reprogrammable FPGA, the RTG4. Each of the spaceware links can go up to 200 megabits per second. One of the main changes of the architecture and improvements are the local power. Now will be powered with 12 volts. Will be included an overvoltage and LCL protection within the board. So it will be very self-contained and modular board. But we also provide backward compatibility with 3.3 volts as a main power supply. Okay. Also, we had to do, as it was pointed out in previous presentation, we had to do some trade-offs at the architectural level, mainly because of the pin multiplexing of the GR740. So we decided to use 4 spaceware links for communicating for command control between the microprocessor and the PA, instead of using any other like PCI interfaces, mainly because the GR740 provides a controller, SDRAM controller, with a single data rate SDRAM. So we consider that we need for some applications the full data bandwidth between the microprocessor and the SDRAM. So we will provide 64 bits plus 32 Reed-Solomon bits for the SDRAM. In that case, if we use in the full data bandwidth, we cannot use the Ethernet port 1 or the PCI interfaces. This is a trade-off we have to do here. But we had the full bandwidth available for the microprocessor between SDRAM and the GR740. Initially, we provide 512 megabytes Reed-Solomon protected of SDRAM. But currently, by using some hardware tweaks and special configuration in the GR740, we could go up to 1 gigabyte SDRAM, which is the maximum memory map that can be available for the SDRAM. We had also an optional SDRAM bank connected to the FPGA, also Reed-Solomon protected with 64 bits and 32 bits for Reed-Solomon, for EDAC. We provided as an optional buffer for particular application of the missions. We provide also a massive amount of NAND flash memory, also Reed-Solomon protected, up to 256 gigabytes. That can be used for non-volatile memory for boot, for application software, or storing scientific data for as a mesh memory. Obviously, storing the boot in the flash NAND will be used for short-term missions because of retention capabilities of the technology of the NAND flash. So in that case, if we need a long-term mission, like a geo missions, we will provide storing the boot in the MRAM connected to the GR740. But we need to know that we use the MRAM from the PROM-IO interface of the GR740. We cannot use it at once, this interface with the CAN bus or MIL bus or even the UART. So we had to do some trade-offs here. In case that all the processing power that provided by the board is not enough for a particular mission, we will provide an expansion connector for putting in a measuring card the specific processing needs in the board. Regarding the debugging interfaces available from the front panel connector, which means the left side of the data block, we provide debugging of the microprocessor by using JTAG or either Ethernet. Also, we provide the JTAG for the FPGA in order to change the code with the unit close. Okay. Regarding external interfaces, which are placed in the left side of the block diagram, we had 2 UART links, 3 spaceware links connected directly through the spaceware router of the microprocessor, CAN bus, a dual CAN bus, and a dual MIL bus. Both buses are not only connected to the microprocessor, but also to the FPGA. So in case that we are using the MRAM for booting, we still have access to those connectors, but not through the microprocessor, but through the FPGA. We provide equipment switch on lines and redundant PPS signals connected to the FPGA, and 8 GPOs and 8 GPIs, 8 GPOs by using a physical layer that can be LVDS or SVDL. So they can be used for either additional spaceware interfaces or additional UART or any specific interface that are required for a particular instrument. Regarding the internal interfaces, they are mostly driven by the ADA standard. So we will have up to 7 spaceware links, which one of them are directly connected to the microprocessor, to the backplane. The other 6 are connected to the FPGA. We will have status and command and control signal, SPI bus, that can go up to 10 megabits per second, dual CAN bus, and a range of GPIs and GPOs connected to the FPGA, so they can be tuned depending on the mission. The ADA standard will also need to use or to have an analog function for housekeeping telemetries acquisition. And we will have high-speed serial links based on space fiber over copper to the backplane. And one of the features that I think that are more interesting for this GR740 evolution is the use of a multi-lane space fiber based on optical medium, composed of 4 lanes. Each lane can go up to 3.125 gigabits per second, which means a combined data throughput of 12.5 gigabytes by using the multi-lane feature of a space fiber. Okay, mechanically speaking, the board has been evolved from a standard 6U form factor to 6U extended, which means that we will have a PCB of around 220 millimeters by 233 millimeters. The pitch has increased from 5 HP to 6 HP, which will allow us to use 2 rows of connector in the front panel, which from my point of view is much more understandable because we can group the signals per function more easily with 1 row. In the figure, we have the new backplane connector will be compatible with AIDA standard. And the optical link, as it is a very specific link for particular instruments, will be connected to the real panel of the unit. Okay, so just to conclude, I would like to show you some notes of the development plan for this processing board. The intention is to at least manufacture 2 full EMs, okay, in order to have a parallel development of the software drivers and the hardware characterization and the FPGA validation. It will be mostly the first EM that will be fully characterized, will be going through thermal cycling in order to achieve a maturity level at least of TRL6. So currently we are working on designing the FPGA of the main blocks needed for the full characterization. We are working on the flash controller and the mass memory controller of the FPGA, boot control through AirMap between the FPGA and the microprocessor. We are working on the high-speed serial links and the time detention function, just to name a few functions that we are working on. Regarding the software design, right now we are working with the GR740 development board, but the intention is also have a dedicated EM for software to validate the driver functions. Right now we are working on the initialization routines, the self-check and application loading, and the hardware-dependent software, not only for the functions that are being developed in the FPGA, but also for the function included in the GR740 processor itself, and in general other functions required for this application. So showing you a timeline, September this year, we redefined the architecture with some improvement, basically the adaptation to ADA standard and overcoming those limitations that we had in the previous architecture, increasing the memory depth of the SDRAM bank and the flash banks, including also the optical links. We prepared a new module specification, FPGA specification, and software requirements. Our intention is to have, in May this year, the MRR for the 2 EMs, and have one of the EMs ready in June and July, the other one for the software. And the last quarter of the next year to have fully characterized one of the EMs, going through a thermal chamber testing. And hopefully we will have ready one of the EMs at the end of the next year with a TRL6 achieved. And that's it from my side. Thank you very much for your attention, and if you have any question, I will be glad to answer you.